Today in Lecture 7, we will cover Section 3.4. At the end of today's lecture, you should be able to construct an expression for the voltage drop across parallel resistors, as well as current division through parallel resistors. You should be able to construct an equivalent resistance for resistors in a parallel configuration, and you should be able to understand and apply the concept of conductance in its relation to resistance. To begin, let's consider a parallel resistor network where we have a current source IS feeding current to resistor R1 and R2. R1 and R2 exist in a parallel configuration. Devices in a parallel configuration have the same voltage potential across them. Let us look at our current source IS. Recall a current source is a variable voltage source. That is, as we provide current, i.e. voltage, to our top node, the positive terminals of R1 and R2 must have the same positive voltage potential. As current runs through R1 and R2, our voltage is going to drop as expressed by V1 and V2. At the bottom, we will have our lesser voltage potential at B. This voltage potential at B has to be the same at the negative terminal of R1 and R2. Thus, our voltage drop of V1 and V2 across R1 and R2 must be equal. Although our voltage potential across our parallel resistors is equal, our current divided between them can differ. That is, I1 and I2 can have differing values based upon R1 and R2. To quantify this, we will apply KCL at node A. Applying KCL at node A, we have IS coming in from our source, and we have I1 and I2 exiting. Now, if we apply Ohm's law to this equation, recalling I is equal to V per R, we can say our source current is equal to V1 per R1 plus V2 per R2. Since V1 and V2 are equal, we set this as V. Thus, we can express our current, IS, as being equal to our voltage potential across our parallel resistors times the quantity 1 per R1 plus 1 per R2. Now we can solve for our voltage potential across our resistors from this equation. That is, our voltage potential across our resistors is equal to 1 per R1 plus 1 per R2 to the negative 1 times our source current. Alternatively, we can express this as our voltage potential is equal to the quantity R1 times R2 per R1 plus R2 times our source current. And we call this quantity R1 times R2 per R1 plus R2 our equivalent parallel resistance, often denoted as REQ or R sub P, where P indicates that this is existing in a parallel configuration. Now, to determine the current through each leg, we will go back to Ohm's law, where current I1 would be equal to our voltage potential per R1. Our voltage potential is just found to be R1 times R2 per R1 plus R2 times our source current, and we divide this by R1. We notice our R1s cancel out, and our current running through R1 is equal to the quantity R2 per R1 plus R2 times our source current. That is, as we're looking for a current I1 running through R1, we place the resistance of our opposing resistor in the numerator per the sum of our resistances in our parallel configuration times our source current. Now, if we look at the current running through leg 2, we see I2 is equal to V per R2, where voltage was expressed as R1 R2 per R1 plus R2 times our source current, and we divide this quantity by R2. Our R2s cancel out, and we notice now R1 exists within our numerator, and the sum of our parallel resistances exists in our denominator. That is, when we're solving for I2, we look at our opposing resistor and place that value within our numerator per the sum of our resistances in our parallel configuration times our source current. Now this leads us to a very interesting expression. We noted Rp to be our equivalent resistance, and this was a consequence of solving for our voltage potential across our parallel resistances. Thus, we can formally state that our equivalent resistance for a parallel configuration, REQ, often denoted as R sub P, is expressed as follows. 1 per equivalent resistance is equal to the sum from I is equal to 1 to N of 1 per R sub I. That is, if we have resistors in a parallel configuration, we sum 1 per to get 1 per R equivalent.